there were laws. Remember, laws are established sets of observations. These observations, these laws came first, and then a theory was developed by Dalton that explained the laws. So the three of the most important laws were the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And these led to modern atomic theory. We talked about Lavoisier and how he burned things in closed containers and weighed the contents before and after. And he found that in a chemical reaction, matter is neither created nor destroyed. That's known as the law of conservation of mass. If you start with 5 Lego bricks in a little sculpture and you take them apart and make 2 new little tiny sculptures, you still have the same mass of Lego bricks. Lego bricks don't appear and disappear. Atoms are not created or destroyed in chemical reactions. So the total mass of the substances involved in the reaction doesn't change. That's the law of conservation of mass. This supports the idea that matter is made of individual particles. Here we have an illustration of sodium metal. And here is a picture of sodium. Sodium is a soft, shiny metal. You can cut it with a table knife. Here we have an illustration of chlorine gas. It's a yellowish gas and it's poisonous. If you combine sodium metal and chlorine gas, they will react and form sodium chloride, which we call table salt. And here's an illustration of what those atoms are doing in the table salt. If you weigh the reactants, 7.7 grams of sodium and 11.9 grams of chlorine will react with each other. That's a total mass of 19.6 grams. If those react, they will form 19.6 grams of sodium chloride. The mass overall doesn't change. How is this possible when one thing, well, 2 things really, you have a metal and a gas, and this is turning into salt. You couldn't eat either of these, and yet we sprinkle this stuff on our food every day. What's going on? Well, it's just a rearrangement of the particles, just like you rearrange Lego blocks when you turn your spaceship into a house. These little purple balls were all next to each other, and now they're going to be interspersed with the little green balls. It's just a rearrangement of atoms. The law of conservation of mass supports the idea of atoms. The law of definite proportions. So in 1797, French chemist Joseph Proust made some observations about compounds. He summarized these observations in the law of definite proportions. A lot of times when we look at the words in a statement like this, it's a little hard to understand, so we always need to have some examples as well. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. This is sometimes called the law of constant composition. So here's an example that hopefully will help us to understand. If we decompose 18 grams of water, which we can do just by passing electrical current through it, we will produce 16 grams of oxygen and 2 grams of hydrogen. That supports the law of conservation of mass. The mass of what we produce is equal to the mass of what we started with. But now we're looking at the relationship between the oxygen and the hydrogen. So if we look at the oxygen to hydrogen mass ratio, we take the mass of the oxygen to the mass of the hydrogen. 16 divided by 2 is 8.0, or we could say the ratio is 8 to 1. No matter where you got the water, you can make water in a lab by combining oxygen and hydrogen. You can isolate water from various sources on the earth. No matter where you get it from, how it's prepared, water always has the same mass ratio. The composition is constant. And this also supports atomic theory. Let's do an example here. 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon. And the other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. That's a word problem. There's a whole bunch of words. Read the words and then look for the numbers. So I'm going to pull the numbers out and kind of label them. First number I come to is 17.2 grams of oxygen and 12.9 grams of carbon. That was the first sample. The other sample was 10.5 grams of oxygen and 7.88 grams of carbon. What does the law of definite proportions tell us about these things? The ratios should be the same. These are 2 samples of the same compound. The ratio of oxygen to carbon should be the same for both samples of it. So we can make a ratio by dividing. So I'm going to go oxygen to carbon for both. 17.2 divided by 12.9. 1.3333 forever. 10.5 divided by 7.88. 1.33248731. Are those numbers the same? I hear a no. They are not exactly the same, are they? These numbers are measurements. There is uncertainty in every measurement, okay? And these were not measured all that precisely, just to the nearest tenth of a gram. So let's use what we learned about significant figures and make sure that these numbers are expressed to reflect the precision of those measurements. So here we have 2 numbers that are being divided. Each of the numbers has 3 significant figures. So then the answer should only have 3 significant figures. So if I round this to 3 significant figures, I have 1.33. There's uncertainty in the second decimal place. The bottom numbers are also 3 significant figures, and so this should also have 3 significant figures, and that's going to round to 1.33. Now are they the same? Yes, they are. They are the same within the uncertainty of the measurements. If this one came out to be 1.34, I would still consider it to be the same or not significantly different from this one because there's uncertainty in the last digit. So it might be off by 1 or 2. Because these mass ratios are the same, these results are consistent with the law of definite proportions. Any questions? Yes?
So there's 3 significant figures because we start off with 3?
Yes. This answer has 3 significant figures because each of the numbers we used in the division has 3. Any other questions? Yes?
Yeah, for like the purpose of testing or graded assignments, are we going to be doing something like that where it's going to be a judgment call, like you said, like you would consider this close enough to be equal?
That's a good question. I want you to always try to apply the rules of significant figures so that your answers aren't ridiculous. This bottom number here, that's a ridiculous number of digits. There will be certain situations, especially on the first exam, where I will be testing you specifically on, do you know how to do sig figs? The rest of the semester, I am going to expect that you use them correctly, but I will not try to trick you with significant figures. So I would not say put one, oh, lost my pen. Like if this was the correct answer to a multiple choice question, I wouldn't also put this number up there just to trick you. Okay. But you should be able to recognize that, 5.743, if that's what your calculator comes up with, and one of the multiple choice answers is 5.744, you should be able to recognize that as an acceptable comparison to this. That your calculator gives you this, and that's the choice. That is really the same number.
But it's not gonna be like this, and then like 5742.
Yeah, I'm not gonna try to trick you. I won't try. Occasionally I trick students unintentionally, and if I do, please tell me about it. Any other questions? A little bit later, just a few years, 1804, John Dalton again published the law of multiple proportions. Just on the surface, that seems to contradict constant or definite proportions. But this is talking about something a little bit different. When two elements, and we're just going to call them A and B, when they form two different compounds, not the same compound, but two different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. That probably didn't mean a whole lot. If we have 1 atom of A, it can combine with either 1, 2, 3, 4, 5, 6. It has to be a whole number of atom B, because like with Lego blocks, you can't have part of a Lego block. You either have the block or you don't. It's like people, right? How many people in the family? It's not 2.75. You can't have 3/4 of a person. They're either in the family or they're not. And so because the atoms combine in small whole number ratios, then when we compare the masses of B that react with a particular amount of A, we're always going to get small whole number ratios. So let's do an example, and hopefully it'll make a little more sense. Carbon monoxide and carbon dioxide. Two compounds of carbon and oxygen. If we look at the mass ratio of oxygen to carbon in carbon dioxide, we did that in the previous example with oxygen and carbon, I believe. Here the mass ratio is 2.67 to 1. That means 2.67 grams of oxygen would react with 1 gram of carbon. That's for carbon dioxide. In carbon monoxide, the mass ratio is 1.33 to 1. So we have two different mass ratios because they are different compounds. If we take the mass ratio of one and divide by the other, we're going to get a small whole number. You always want to divide the larger by the smaller to get a whole number. Carbon dioxide has 2 atoms of oxygen. Carbon monoxide has 1 atom of oxygen. So the ratio of the masses has to be 2 to 1 because the numbers of atoms are 2 to 1. And so the law of multiple proportions supports the theory that matter is composed of atoms. Any questions? Hydrogen and oxygen form both water and hydrogen peroxide. The decomposition of a sample of water forms 0.125 grams of hydrogen to every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 0.25 grams of hydrogen to every 1 gram of oxygen, Show that these results are consistent with the law of multiple proportions. So again, I read all the words, so many words. Let's look at the numbers. 0.125 grams of hydrogen for every 1 gram of oxygen. That's for water. And for hydrogen peroxide, it's 0.250 grams of hydrogen to 1 gram of water. I'm sorry, 1 gram of oxygen. So here the ratio is 0.125. Here the ratio is 0.25. The law of multiple proportions says that the ratio of the two ratios should be a whole number. You want to take the larger number and divide it by the smaller. So 0.250 divided by 0.125 equals 2. If the ratio of those two ratios comes out to be 2, 3, 4, 5, 6, a small whole number, then it supports the law of multiple proportions. Any questions?
Because they have to put like bones in them and like weights.
It's because they contain the same two elements, and the difference between them is the number of atoms of one of the elements.
You would never get a non-whole number.
No, you'll never get a non-whole number. So, let's just think about Lego bricks. Let's think about like giant Lego bricks, and let's say that each of these blue Lego bricks weighs 1 gram. And here we have a compound. All the red ones weigh 2 pounds. Maybe I should make it longer if it's heavier. So that one's 2 pounds. And then this compound has 2 red Lego bricks. What we're doing when we're doing all this funny math stuff is I'm taking the ratio of the mass of the red to the mass of the blue. So that's going to be 2 to 1. Yeah, 2 pounds to 1 pound. And in the other compound, I'm taking the mass of the red. Here there's 4 pounds of red to 1 pound of blue. And then I'm going to take those ratios, the larger divided by the smaller, and it ends up to be 2. You can't have a fractional number, because to do a fractional number, you'd have to have part of a Lego block. So law of multiple proportions gives whole numbers because you can't have part of an atom. You have a whole atom. Okay? Any other questions? Yes.
So back to that, say you had like 10 grams of water.
Mm-hmm.
It would also mean that you have 12.5% of that 10 grams of hydrogen. No matter how big the sample of water you would have.
Right. The law of the law of definite proportions tells us the ratio of oxygen to hydrogen mass will always be the same. So if my sample of water here is larger, if I have 10 grams of oxygen, then I'm going to have 1.25 grams of hydrogen. Everything would be multiplied by 10. But the ratio, the proportion is the same. It's a good question. Yes?
It seems to me like it should be the other way. 125 should be for water.
That's a good question. He says it seems like it should be the other way, that the 125 should be the water.
Because there's 2 more oxygens on that peroxide over, and 1 less. There should be less weight of hydrogen per oxygen in the peroxide than hydrogen in the water. No?
Yeah, I hear what you're saying. I definitely hear it. Let's go with green here and think about this. We got H2O and H2O2. I'm going to pause. So, very perceptive student has found an error in the example in the textbook. The good news is that all the math is fine, and we just need to ignore the words water and hydrogen peroxide and just say maybe a sample of A and a sample of B. But yeah, I'll be revising this slide for next semester. Okay, John Dalton, the atomic theory. So John Dalton's theory of atoms, the atomic theory, explains those laws. And these are the four components of the theory. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms of elements are different from one another, but atoms of the same element are the same. Atoms can combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. Now, as I mentioned in chapter 1, sometimes theories need to be revised when we learn more. There's a couple of things in this original theory that we now know aren't quite true. I have a relationship with the freight trains. Today, yeah. Yeah, don't close the door though, because it's 78 degrees in here and it's 79 now and we're just dying. Can anybody point out one of these things that isn't quite true? The fourth one, atoms of one element cannot change into atoms of another element.
Stars use fusion to achieve that.
Yeah, in a nuclear reaction, atoms of one element do change into atoms of another element. But that's in a nuclear reaction. And that's like playing with Lego blocks with a sledgehammer, right? It's not normal. So in chemical reactions, in stuff that might happen in this room, that doesn't happen. It's like playing with Lego blocks with your hands. You can rearrange them, you can combine them in different ways, but the individual atoms remain intact. There's two others of these that are a little not quite right. The first one, atoms are indestructible. Well, no, you can destroy atoms. You can smash them. You can divide them into other atoms, and that's nuclear weapons.
And then postulate 2 of isotopes.
Yes. Number 2, atoms of a given element have the same mass. Well, we're going to learn in this chapter that there are isotopes and that there are little slight different versions of atoms within an element. In carbon, there's carbon-12, carbon-13, and carbon-14. When he developed this theory, they didn't know about that yet. So does that mean we throw out the whole theory? No, we just have to make some little tweaks to it. Any questions? I'm not going to make you write down all the postulates of the atomic theory on a test, but you should be familiar with these ideas.